Welcome everyone. In this lesson we're going to be talking about the definite integral. So we're going to kind of build off of our idea of the antiderivative and indefinite integrals, and we're going to introduce something new. And we're going to see how to calculate it. So let's start with the notation. So our definite integral is going to be this gadget right here. And the way we read this is the integral from a to b of f of x, and we're integrating with respect to x. So it's very similar notation to what we saw with an indefinite integral. The only difference is now we're going to have some numbers on our integral sign. And what do those numbers represent? Well, what we're going to be doing is we're going to be looking at this function f. And in order for our definite integral to work out nicely, we're going to assume that function f is continuous. It's a continuous function, and we're going to be looking at an interval from a to b. So that's where these a and b values come. We're kind of looking at a section of our function f of x from a to b. And we call those, on our integral sign here, we call those the lower limit and the upper limits and the upper limit. And together we call these the limits of integration for our definite integral. All right, so this is what we're going to be calculating, the definite integral. Later on we'll see kind of what this thing actually represents. But first we're just going to get some practice calculating it. And the way we're going to calculate it is by using the antiderivative of the function. And so what we do is we take the antiderivative, we plug in the upper limit, then we take that same antiderivative, we plug in the lower limit, and we subtract. So we're going to think of this as like a two-step process. How are we going to calculate our definite integral? All right, so this is what we're going to have. We'll have some function in here, and then we'll have some numbers, a and b, on our integral sign. And the first thing we do is we're going to figure out what the antiderivative of our function little f is. So that's going to be step one. Find the antiderivative. All right, so that's the first thing. Well, once we have our antiderivative, then we're going to have a vertical line here just to remind us that we're going to evaluate. So this vertical line essentially means evaluate. And we're going to put the lower limit on the bottom and the upper limit on the top. So x equals a and then x equals b up here on the top of our vertical line. And then once we have our antiderivative, then we're ready to evaluate. So step two is going to be evaluate. So when we do this, the order does matter. So we're going to take the top number, plug it into our antiderivative first. Then we're going to take the bottom number, the lower limit, x equals a, and we'll plug it into our antiderivative second. And then we subtract. So when we do this, the upper limit or the top number goes in first, then the bottom number goes in second, and then we subtract the two. So the order actually does matter here because of the subtraction. So that's step two. And this is basically how our work is going to look. All right, so with this in mind, we've talked about antiderivatives and indefinite integrals, and there is a subtle distinction between the two. So when we do indefinite integrals, this is what we've introduced so far. We have an integral sign, a function we're integrating, and then our differential dx telling us, what the variable is that we're integrating with respect to. And when we get our answer, the result should be a function. So there should be variables in there. And when we do this, we want to use plus c in our answer. Okay, so we've seen that before. What's going to happen with definite integrals? So with definite integrals, similar notation, but our answer, the result, is going to be a number. So the only difference here is we still have our integral sign. We're still going to have our function. We have our differential dx telling us what variable to integrate with respect to. But now we're going to have these limits of integration on our integral sign. And that's telling us, really, that when we do this, the result should be a number. So we should get a number as our answer. And when we do our work for definite integrals, we don't have to use plus c. So we don't have to use that plus c in our work. Why not? Well, it turns out it just cancels out. So let's suppose that we have two antiderivatives. So let's say we have capital F of x, and then maybe some other one, capital F of x plus some constant c. And let's compare what would happen if we took the one with plus c and evaluate it from x equals a to x equals b. So let's take that antiderivative with the plus c at the end, and let's see what happens when we plug in b and a. Well, when we do that, top number goes in first, so we would end up with f of b plus c. Then the bottom number goes in second, so we'd end up with f of a plus c, and then we subtract. And then when we do this, if we look in the first part here, we have a plus c. And then if we look in the second part, there's also a plus c, and then we're subtracting. So those are just going to cancel out. And what we're left with then is just capital F of b minus capital F of a. And that's the same result that we would get if we took just our antiderivative without the plus c and evaluated it from a to b. So the plus c here, it's helpful for indefinite integrals because we don't necessarily know which constant we would need to use, but for definite integrals, that constant doesn't really matter because it's going to get canceled out. And you can kind of see that graphically because what we're doing when we look at this change in our antiderivative, let's suppose that we are looking at the change from 0 to 1. So we have our first graph here. Let's suppose that our interval was from 0 to 1. Well, what this change in our antiderivative is measuring is it's just measuring this vertical height. Yeah. Let's clear that up a little bit. So that we're just measuring this vertical height. And if we looked at the one with plus c, well, we'd be looking at this vertical height, and they're the same. So, whether we shift it up or down doesn't really matter because we're just kind of looking at the relative change here. So whether we look at this change with plus 0 or whether we look at this change with plus 1, doesn't matter. The constant would cancel out. All right, so just something to keep in mind as we're doing these. So let's try an example. Let's look at example 1. We're just going to try some basic definite integrals here where the function we're integrating is not too complicated. So let's look at this first one. We have the integral from x equals 1 up to x equals 2, and the function we're integrating is just the function x. All right, so our first step, how are we going to calculate this definite integral? Well, the first step is we have to find our antiderivative. So that's what we're going to do. The function we're integrating here is x. So we're going to get our antiderivative of that. And this is power rule. So even though it's not written, there is an exponent here of 1. So we could throw that in if it helps. And then if we do power rule, our variable is x, so we're going to keep our variable the same. We're going to add 1 to the exponent, so we go from 1 up to 2. And then we take this new exponent, flip it, put it in front, so 1/2. And then this is our antiderivative now of the function x. And once we have our antiderivative, we put this vertical line with x equals 1 and x equals 2 to indicate that our next step is to actually plug in and evaluate. And that's step 2. We're going to evaluate our antiderivative where we plug the top number in first, the bottom number in second, and then subtract. And when you do these, it helps set up a nice big set of parentheses for what you get when you plug the top number in. Then set up another nice big set of parentheses for what you get when you plug the bottom number in. And then we're going to have our subtraction there in the middle. All right, so what do we get? Let's take 2, our upper limit, plug it in. We end up with 1/2 times 2 squared. Then we take our lower limit, 1, plug it in. What do we get? We get 1/2 times 1 squared. And again, the order matters here. So because we have that subtraction in the middle. And then if we clean this up, simplify, we end up with 1/2 times 4, which is 2. And then over here we end up with 1/2. And that simplifies to 3/2. And you could see our answer here is a number. And we didn't have to use that plus c for our antiderivative. All right, so that's really the idea. Let's try another one of these. So let's look at the next one here. So for this one, the function we're integrating is e raised to the negative t. And our interval, we're going from -1 to +1. All right, so the first thing we got to do is we got to get the antiderivative for this exponential function. And if you don't see it right away, it might be helpful to write this as e raised to the -1 times t. And we had an exponential rule that said e to the kx dx, the integral of e to the kx, is 1/k e to the kx, plus c when we're talking about just regular antiderivatives. So the k value for our particular function here is this -1. So if we find the antiderivative, it's going to be the antiderivative of this exponential function stays exactly the same, so it'll be e raised to the -t. Then we take this constant that's in front of our variable here, and we flip it and put it in front, so maybe 1/-1. Now for definite integrals, we don't have to worry about this plus c business. But we do have to put this vertical line, which means evaluate. And we're not using x anymore, we're using t. So those should be t equals -1 and t equals +1. All right, so this is our antiderivative, where we're using this special exponential rule. So we keep the exponential function the same, and then we take that constant that was in front of t, and we flip it and put it in front. Now, when we do this, it helps to simplify the antiderivative down as much as you can before you go on. So I would write this as negative e raised to the -t. Just to make the evaluating a little bit easier. And once we're there, now we're ready to plug in. So the next step is just evaluate. So when you do this, again, it helps set up some nice parentheses here for what you get when you plug the top number in and what you get when you plug the bottom number in. And so when we do this, let's take the top number, plug it in. We're going to end up with negative e raised to the negative 1. So I'm going to just plug the 1 in. And then I take the lower number, plug it in. I'm going to end up with negative e raised to the, and then we're going to have a double negative, so that'll become positive 1. And if we simplify this out, not too much to simplify, but we do have a double negative. So we do have a double negative here, and then we don't normally write an exponent of 1. So if I was going to rewrite this, I would have negative e raised to the negative 1 plus e. And perfectly good to leave it like that. But I think it's helpful to kind of take the positive number and move it in front, just so you don't lose track of that negative. So I would probably write this as e minus e raised to the negative 1. And there we go. Another number. And don't forget, e is just a number. So even though these look kind of complicated, these are just numbers. So there shouldn't be any variables here once we do all of the evaluation. But once you're getting the hang of these, or when you get started on these, you can also just leave it like this. You don't have to try to simplify it down. But it does help to try to get that practice of simplifying these down, just to make things a little bit easier in case we have to do something with this definite integral. All right, so what we're going to see in class is that there's some properties that our definite integral has. And a lot of them get inherited from the indefinite integral. So we're going to see these properties in class, and they're going to kind of allow us to integrate more types of functions where maybe we have some terms that are getting added or subtracted. Maybe we have a constant multiple in front. But we'll see that in class. So we'll see you then. Bye-bye.